Boom, population genetics. Now we're going to talk about the impact of immigration and emigration on a population. And maybe we'll play musical chairs. I think I might do that. We're going to describe genetic variation and how it relates to natural selection, talk about selection and drift, especially drift in this one, and how selection can lead to adaptation. Migration occurs when populations, get this, migrate between populations with different alleles. So you can get gene flow. Here we've got some brown bugs moving into a new population of green bugs. And once that happens, the allelic frequencies of brown change in the population. That's migration, movement. So in a natural population, just out there in the world, this can be the result of either immigration, organisms coming into your population, or emigration, organisms leaving your population. So the rate and direction of the migration, as well as the starting allelic frequencies, can impact the genetic change. So what that means is, let's say you start off with half and half. You got a population that is 5 out of 10 are brown, and 5 out of 10 are green. Our allelic frequencies then are going to be, in this case, actually let me rewrite this so it's a little bit more apparent with genotypes. Over here we've got big A, 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 big A. All of them are brown. Over in this population, a bunch of little a's. All of them are green. Still, we have a frequency of 1.0. If I was to have an organism moving from the brown population to the green population, and an organism moving from the green population to the brown population, suddenly my frequencies have changed. Now I've got 0.8 green, 0.2 brown in population 2, and 0.8 brown, 0.2 green in population 1. I've changed my allelic frequencies. Evolution has occurred. Now, migration serves to minimize differences in allelic frequencies. Here we had a big difference of 1.0 brown, 0 green, 1.0 green over here, 0 brown. Migration is going to start bringing them closer together. So as the frequency, as migration increases, allelic frequency changes, differences decrease. Here we've got birds on either side of a mountain, blue birds here, red birds over there. If a blue bird flies over there, we've changed the alleles. But if the blue birds and the red birds are able to fly over always, back and forth, with freely, you end up with one unified population. You could probably say that the Richmond area is one population, because you have a lot of movement all through, 288, around 295, there's a lot of movement. You guys can, in fact, find people that are closer than walking distance to you to mate with, right? It's unlikely, though, that you're going to find somebody overseas that you have to get on a plane and fly to. That's a much harder migration effect. You could do it. We're going to see likely lower, similar allelic frequencies in, like, I don't know, what's this area around the school called? Midlothian? Okay, and then what's the Midlothian and Chester? There we go, 2 campuses. You're going to see lower allelic frequency differences between Midlothian and Chester than, say, between Midlothian and China. Does that make sense? All because you can have that easy migration. You might have what's known as assortative mating. With assortative mating, you tend to mate with something that looks like you. Or you tend to forcibly, not forcibly, but you tend to force yourself to mate with something that looks very different than you. Individuals of similar phenotypes are more likely to mate, leading to increased homozygosity. Same plus the same equals the same, and this is the principle behind dog breeding. If you have two purebred dogs, you put them together, you expect the offspring to look like those two dogs. A beagle plus a beagle equals a beagle. I don't know, a Great Dane plus a Great Dane equals a Great Dane. Chihuahua plus Chihuahua equals Chihuahua. Does that make sense? You'll have a lot of homozygosity, which means the alleles will be the same. You might have assortative mating, where individuals of different types are more likely to mate, and that leads to increased heterozygosity. A Great Dane plus a Chihuahua equals who knows. You're going to have a lot of different alleles there. There's not going to be much homozygosity. Yeah, with dogs, if you take two dogs that look different and put them together, you're going to get a wide range of dogs. Inbreeding is a concept that comes about when you have two organisms that are genetically related mating. This leads to increased homozygosity. So here we've got two parents, one of which is afflicted with a recessive condition. They have offspring. Those offspring will be carriers. If those offspring were to outbreed, mate with somebody outside of the family, it's unlikely that that third generation will have the condition. They might be a carrier for it, but they probably won't have the condition. However, if you were to have two carriers mating, you will have a 1 in 4 chance of getting that condition. These values, the chances of finding carriers of a rare genetic condition, increase a lot if you're mating within the family. So inbreeding ultimately increases homozygosity. This image gives you an idea of what happens more likely in nature. You do get a mutation, but that mutation doesn't cause a phenotypic change in the first generation, in the organism that mutated. Let's say that this is snakes. You have a mutation that causes lack of coloration. It's only going to happen on one allele. So you've still got that dominant allele to cover it. It's the next generation, where you've got 3 snakes born from that cross, that if those offspring mate, that's where you really start to see those phenotypic effects. You guys have probably heard of inbreeding before, right? Inbreeding is pretty much not a good thing, right? Dogs inbred, it's a hip disease. So when homozygotes end up having a lower level of fitness, that's called inbreeding depression. We've got these horses that get inbred. They produce an offspring that has a lower fitness level than the original. You have depression. Inbreeding depression is a real and serious condition. Humans have inbreeding an awful lot. We've studied inbreeding for generations. Intermarriage of cousins and close relatives was very, very common in human history. One, because if you're living in an area, a small area, before the advent of mass transportation, likely you're not going to find anybody who's not related to you in some way to mate with. Small populations tend to mate within themselves. True story, when I was living in Danville, those people who lived there never left. There are some people who never went into North Carolina their whole lives, and they live 3 miles from North Carolina. There was not much gene flow into or out of the population. Literally, they had to do some research before they dated anybody in order to figure out if they were related to them. It was an issue. You guys live in a more cosmopolitan area. It's unlikely that you're going to accidentally stumble across a cousin. It's like that in Cumberland? Yeah. Everything is really tightly related. So you have to do some research. So fun inbreeding story with me, which is weird. So when I was 16, 17, I went to Portugal for a summer. My family's from Portugal. So that's the caveat. My family's from Portugal. Small town called Goiás. So went over there, and because I was young and out of the country, I was like, I can meet girls because now I'm the foreign one. It didn't work out that way. I met a girl, though, and I was like, oh, she's really cool. And she's like, yeah, let's get together later. Well, I got together with her later at dinner because apparently she was my cousin. And I was like, huh, let's never speak of this. We didn't do anything. It was just like, you start talking to somebody like just randomly, and you're like, hey, you're pretty cool. I kind of like you. Turns out I was related to her. So always do your research when you're going and finding, your family roots. This image here is of Charles Darwin, who married his cousin. The more you know. Think about the dynasties in Great Britain. The royal family there is famous for having hemophilia, a genetic condition that is it's fairly rare, and it's autosomal recessive. The only way you get it is by having 2 copies of that allele. Well, because of all of the inbreeding, cousin to cousin, in order to secure alliances, that condition has been passed one generation to the next. Now, the current royal family is doing a much better job of outbreeding, which means that their children are not going to have those issues. Now, here's the deal. We're always taught inbreeding's bad. And I'm not one to sit here and defend inbreeding. But when a culture or group first begins to inbreed, embedded within the human genome are what are known as lethal alleles. These are genes that will kill you if you have them in the homozygous condition. If you have 2 alleles that are the same, you die before you're born. The embryo does not develop. So if this is one way that animals have in place to prevent inbreeding. If you were to, or not you, let's say 2 puppies were to accidentally mate with each other and they're siblings, it's unlikely there would be many offspring produced from that because the lethal alleles would knock them out. That reduces the fitness of the population, and that leads to inbreeding depression. Now let's take that one step further. Oh, you scientists, you think about it from a scientific perspective, not from a cultural perspective. Now, you guys have taken sociology and everything, so you know that part. Here's the deal. If you have 2 puppies that are siblings, and they breed, and they produced only 2 puppies instead of 5, what does that tell you about the 2 puppies that are produced? It doesn't mean they're going to be messed up. That means they don't have the lethal alleles. So if they don't have the lethal alleles, and then those 2 puppies mate with each other, what's going to happen? There's not going to be a problem because there are no lethal alleles. 3 generations. Within 3 generations, you can go from a normal society to an inbreeding society and get rid of the lethal alleles. That's how human society was able to last so long with inbreeding, because we didn't have those lethal alleles. However, introduce a new population, introduce a new migrant with new alleles, and suddenly that resets the clock because they've brought with them new lethal alleles. So once you start having inbreeding after that, you have to go through all that inbreeding depression again. Inbreeding was a big thing, and it still is a big thing in many other countries. Societal inbreeding, yes, you've gotten rid of those lethal alleles, but it's used for keeping property in the family. Does that make sense? You own something. You have a daughter. You want your stuff to stay in the family, so your daughter marries your brother. And that keeps everything in the family line. I know you're all totally disgusted by that, but it's called societal inbreeding. And it's just the idea that different cultures have different taboos. Inbreeding becomes a major issue, like we talked about with dogs, where you get hip dysplasia, all these lethal, semi-lethal conditions. It's also a big problem in managed species. Managed species is one that's about to go extinct. Inbreeding depression among the few last individuals of that population can cause the entire species to go extinct. So what might happen in this case is a scientist could introduce a closely related species. And that closely related species could mate within it to lead to some outbreeding and then produce fitter offspring. Well, here's the problem. Few issues. If I was to take, real life example, the ibex. There was one ibex left. It was a male goat. It was a male. It wasn't a goat. One ibex left. It was a male. The ibex is a very, very large goat or ram type creature. All right? Couldn't mate with anything. They found that it was able to mate with a female goat. Successfully, they produced an offspring. That was an outbreed. That was an extreme example of outbreeding. But here's the question I have for you and what we're going to get into in the next several lectures. The offspring that was produced, is it an ibex or is it a goat? Say that again? It's a hybrid of some kind. It could be a new species. How do we define a species? We have these ideas of what we think something is. We try our best to do stuff to protect species. But in the end, it all comes down to definitions, and they're definitions we create. The ibex is extinct now. The last ibex died. The way the last ibex died, not kidding, is we had done our best to save this ibex. It didn't die of disease or anything. It had its own preserve, a very large area that it was just for it, and it had a herd of goats with it because it didn't want it to be lonely. So there's the ibex. It climbs to the top of this hill where there's a tree, and it goes and it's under the tree for shade. And I kid you not, the limb of the tree breaks and falls on the ibex and kills it. That was the end of the species. Yeah, that's right. That's
just Mother Nature's way of saying it's time.
That's the time. So we've got all of these organisms. We've talked about migration, immigration, natural selection. That leads us up to this idea of microevolution. This is the change in the gene pool from one generation to the next. Microevolution is what we can study in the lab. Microevolution is allelic frequencies change from one generation to the next. If you have a change in allelic frequencies, you have evolution occurring. In order for that microevolution to occur, you need genetic variation. Give me one way to get genetic variation. We've talked about it today. What? Migration, that's one way. Another M word. Mutation, there's another. Migration and mutation will bring genetic variation. You've got to have a mechanism of evolution that affects the prevalence of alleles. Give me one mechanism that can affect the prevalence of alleles. Predators, so natural selection. Sexual selection. Heck, any of the selections will impact the allelic frequencies. The cumulative effect of microevolution, one generation to the next, of allelic frequency shifting, based on diversifying selection, balancing selection, stabilizing selection, or directional selection, will lead to macroevolution. This occurs above the species level. It's all of those microevolution effect, and it leads to new groups of organisms being formed. Another concept I want to talk about is what's called genetic drift. Genetic drift is also known as survival of the luckiest. Genetic drift is where allelic frequencies will change from one generation to the next due to pure and random chance. Things happen. It's not because you're more fit. It's not because you can breed more often. It's simply because something happened that prevented you from getting your genes to the gene pool or allowed you to do it more efficiently. Random freaking chance. Genetic drift also occurs on those genes, or those alleles that are not impacted by selection. You guys remember introns and exons? So if you've got an intron, this is all on RNA, right? For RNA, you've got sections that are called introns and sections that are called exons. And what will happen is at the spliceosome, the exons are spliced together, and the introns are cut out. So if you have a mutation in the intron, it's never, ever going to be expressed. You can still have an allele there. Those alleles, though, will not be impacted by natural selection. It's pure random chance. We have a lot of variation in our alleles in our introns. In fact, you've heard of DNA fingerprinting? Most of that variation is in the introns. Most of the variation we're looking for is stuff that happens unique to you that's caused by just sheer random chance. Small fluctuations that occur due to chance. For instance, let's say, I don't know, usually I've got at least, okay, you've got blue hair, good. Right here, the only blue hair allele in the classroom, right? If there was random mating, there was a chance that the next generation would have blue hair. Good on that? If these ceiling tiles, due to random chance, collapsed, crushing her, that allele is gone now. The frequencies have shifted. Those are frequencies due to random chance. Genetic drift has a huge impact on a small population. The one person with blue hair is dead by accident. In a much larger population, 11,000 say, there's going to be a lot more people that have blue hair. It's going to have a smaller impact. So genetic drift is just due to random chance. There are some examples of genetic drift that are super awesome. Genetic drift can occur when you end up with organisms that are being introduced into a new environment. Small group of organisms. It's called a population bottleneck. You take a large group, thanks for being here. You take a large group and let's say there are about 30 people in here. So we got 30 people in here and one of them has blue hair. So it's a 1 in 30 chance. That makes sense? That's our frequency, 1 out of 30. So what, 0.03, something like that? That's the frequency of blue hair, 0.03. If we were to have random breeding under Hardy-Weinberg, you're going to have a very low chance of getting blue hair. Now, if you guys decided, this group of 4 here decided to go off and start a new population, you go on a raft, you start a new population, suddenly now it's not 1 out of 30, it's 1 out of 4, 0.25, which means your frequency of blue hair in that new population will go up. Think of Scotland. Scotland's known for red hair. It's got more red-headed people than just about any other area in Europe. Because those who colonized Scotland, and Ireland too, had that red-headed gene. So a small boatload of people landed there. You had that one mutant, rather than being among a group of 100,000, is now among a group of 30. So when they start to populate the area, when they're interbreeding, that allele goes way up in value. It's a bottleneck. Another cool example of that is, an extreme example of it is, do you guys ever heard of Krakatoa? Okay, Krakatoa was used to be an island. It exploded. It was the loudest sound ever heard on Earth. It was heard halfway, like literally halfway around the world. Krakatoa, it wasn't our fault. Like, for once, it's not our fault. It was a volcanic island that just literally, there were some ships that landed there. They got provisions and they left, and the next day, it exploded, and it was gone. They went back, and there was no island anymore. Over the following 20, 30 years, lava had come up out of the sea, and you'd formed a new island, conveniently now called Krakatoa. So you have this island made of volcanic ash and magma. Rock. Not much lives there. It was wiped down to the floor. First thing that arrives on this island are fungus and sand. You know, you start to build a soil. Second thing that arrives are seeds on the wind. Well, as seeds are landing, now you've got a nice place for birds to land, right? I mean, these seabirds, they're totally protected there. There are no predators, no snakes, nothing there. As the birds are there, they're eating fish from the sea, they're dropping their feces and creating a really nice soil, so you're getting good plants. Life is good. This place becomes a green haven for seabirds. Millions upon millions upon millions of seabirds landing there. Until probably about 30 years ago, 40 years ago, there was a storm. And in that storm, a piece of driftwood was launched into the sea with a, not kidding, Komodo dragon on it. Komodo dragon, it's amazing that we've pinpointed this. So after the storm, a Komodo dragon is hypothesized to have been on a piece of driftwood and floated to Krakatoa. It happened to be a pregnant female. Behold the promised land to this Komodo dragon. Monitor lizard, just a Komodo dragon monitor lizard is about a 12-foot long lizard. Lizard. And it just goes about eating all the birds. Not all of them, it's only one. So it starts eating the birds, lays its eggs, its offspring hatch, and they start eating the birds. What ends up happening then is the Komodo dragon population goes way up, but they all have the same genetic background. They all have the same genes. It's a super tight example of population bottlenecking. So I thought it was really cool. This happens well, bottlenecking happens a lot, and there's a lot of bottlenecking that we've done. Corn, cows, all that stuff, we've chosen those particular genotypes, and then that's all that's really left. But think about, we hunted the walrus until there were only 200 left. The walrus population has a lot of genetic homozygosity because of that. The whale population, same thing. Anytime we get a population really low, and then we're like, hey, we got to protect it, the population numbers may go back up, but the allelic frequencies never really get fixed. Yes?
Didn't wolves go through a bottleneck?
Wolves went through a bottleneck. Heck, deer almost went extinct in the continental United States. Deer, during the last ice age, they were confined, literally, they died out on the mainland. They happened to be on an island, and then they swam from the island back to the mainland and repopulated. Yeah, deer swim. All right.